Hello everyone, I am Sijun Huang from National Kaohsiung University of Science and Technology, Taiwan. Today, I want to talk about an image segmentation algorithm using graph-based formulation. This algorithm was proposed in IJCV 2004. The outline of this lecture includes introduction about goal and the idea of the proposed algorithm, graph-based formulation of segmentation problem, partition strategy used for segmentation, and the proposed segmentation algorithm. Image segmentation is a process to partition an image into a set of disjoint regions. For example, the picture on your right-hand side is a segmentation result of the image on your left-hand side. Different regions are labeled with different colors. The purpose of segmentation is to promote the image description from pixel level to region level so as to facilitate the process of addressing a wide range of the vision problems, such as motion estimation, image indexing, or object detection. In the segmentation literature, they generally assume that regions have nearly constant or slowly varying intensities. However, this assumption does not hold in some cases. A picture provided in this paper illustrates this phenomena. From human perception, this picture is composed of three regions. The first one is the region with intensity ramp. The second one is the region with constant intensity. The last one is the region with a high variability. Segmenting this picture based on the above assumption will result in only two regions. This is because the first and the second regions have similar intensity variation, so that they will be merged together. Additionally, in order to obtain the good segmentation as human perception, the determination of boundary between two regions cannot only use local decision criteria, but should be from more global view. For example, a pixel label in a red circle will be determined as a boundary point from a local view because it has large intensity difference among its neighborhoods. But it will not be a boundary point if from a more global view. Accordingly, the main objective of this work is to develop the segmentation algorithm that captures perceptually important regions that reflect global aspect instead of local aspect. In addition, it should run efficiently in time nearly linear in the number of image pixels, so that it can be broadly useful in many areas. To achieve this, the idea of this work is to use criteria instead of a constant value to adaptively determine if there is a boundary between two adjacent regions, Ci and Cj. This boundary exists if the distance between two regions, called the between distance, is larger than the variation within regions Ci or Cj, called the within distance. Before to detail the proposed segmentation algorithm and define the between and the within distance, we firstly talk about how to formulate the segmentation problem using graph. Let G is an undirected graph, which consists of V and E. V is a set of vertices. A vertex in V denotes a pixel. E is a set of edges. A edge in E links a pair of neighboring pixels. Furthermore, each edge is associated with a weight W. denoting the dissimilarity between neighboring vertices Vi and Vj. For a tiny 4x3 image, it has 12 pixels, and correspondingly, vertex set V consists of 12 vertices. That is, a pixel corresponds to a vertex. As for modeling edge set E, it depends on which neighborhood system you use. N4 and N8 are two commonly used neighborhood systems in the image processing area. N4 means a pixel has 4 neighborhoods at its top, bottom, left, and right. N8 means that a pixel takes its adjacently surrounded pixels as its neighborhoods. On their left-hand side are the graphs using N4 and N8 neighborhood system, respectively. For the weight associated to the edge, it is generally defined as the absolute of intensity difference between two vertices. For example, the two weights associated with these two edges are 1 and 28, respectively. Based on describing an image using graph, the image segmentation problem becomes to partition the vertex set V into several components, C1, C2, and so on. Here is an example to segment the aforementioned graph into 3 components, C1, C2, and C3, each of which is with different colors. Although there exist many segmentation algorithms, all of them use the same criteria for segmentation. Vertices in a component should have a similar intensity, but different across different components. In other words, edges between two vertices in the same component should have lower weights, but edges between vertices across different components should have higher weights. After introducing graph-based formulation, we then define the Within difference of a region called the component. Within difference is referred to as internal difference in this paper. As mentioned before, it measures the intensity variation within a component C and is defined as the largest weight in the minimum spanning tree of C in this paper. Internal difference of C is equal to 0 if C has only 1 pixel. Next, we define the difference between two components called the component difference. Component difference of Ci and Cj is defined as the minimum weight of edges connecting Ci and Cj. This term becomes infinite if there is no edge connecting Ci and Cj. Here is an example to illustrate the definition of internal difference and the component difference. For a component C1, all the edges in its minimum spanning tree are labeled with the border green lines. The internal difference of C1 is thus the maximum value of the weights of these border lines, which equals to number 2. For the components C2 and C3, there are 2 edges between them, whose weights are 65 and 55. Thus, the component difference between them is the minimum value of the 65 and 55. Next, we talk about the criteria for evaluating the boundary evidence between a pair of adjacent components using the defined internal and component differences. The equation here is the same as before in mentioning the adaptive criteria. There is a boundary between Ci and Cj if their component difference is larger than the internal difference of Ci or Cj. This equation can be further re-expressed as the following equation, which uses mean operator to replace all operator. However, the defined predicate is not a good estimate of local property because it makes the algorithm tend to have small components. For example, in the extreme case, when a component has only one pixel, its internal difference is equal to 0, that will be always smaller than the component difference. This makes the segmentation algorithm result in many small components. To compensate this paper introduced a term called the threshold function tau based on component size. Here, tau of component C is defined as a given constant k over the size of C. Accordingly, the original equation for boundary predicate can be rewritten as this equation. Next, we will give a tiny example to detail the overall segmentation algorithm using this defined boundary predicate. The input of the segmentation algorithm is a graph G with n vertices, m edges, and a constant parameter k. And the output of the segmentation is a partition of V into several components. During the initialization, each vertex is considered as a single element component. Since each component only has one vertex, its internal difference is initialized to 0. Then, we sort all edges according to their weights in a non-decreasing order. The weight here is defined as the absolute of intensity difference. For example, the numbers in blue color are the edge weights. After sorting, the number in the green circle denotes the order of the edge. After initialization, we proceed to the iteration step by firstly taking an edge according to its order. Let EQ be the selected edge. Vi and Vj are the two vertices of EQ and respectively in Ci and Cj. If Ci is not equal to Cj, we do the following steps. If the boundary predicate of Ci and Cj is false, means that there is no boundary between them. So we merge them together and set the internal difference of this merged component as the weight of EQ. After that, we move index to the next edge and go back to the step 1. Before detail the iteration steps, we further discuss the equations of the merge condition. According to the prior discussion, the boundary predicate is true if the component difference of Ci and Cj is larger than this term. In other words, it is false if the component difference is equal or less than this term. And this term can be rewritten as the following one. Since EQ is the edge connecting Ci and Cj, and with the smallest weight we see so far, they should be merged together if the weight of the edge EQ satisfies these two equations. Using this merge condition derived from boundary predicate, we give an example to detail the iteration steps of the segmentation algorithm. In this example, with constant parameter k equal to 100, the first selected edge is this one. Since his weight satisfies the merge condition, so we merge them and set its internal difference as 0. For the next edge, its weight is equal to 1 and also satisfies the merge condition. So we merge them and set the internal difference to the current edge weight equal to 1. We do the same thing repeatedly. Take a next edge, check the merge condition, and do the merge. Update the internal difference. Take a next edge again. Check the merge condition and do the merge. Update the internal difference. So far, we obtained a segmentation with 3 components. Now the edge we take to process is with the weight equal to 24. But it violates the merge condition, so the green and the red components will not be merged. Finally, after completely visit all edges, we obtain a segmentation result with 3 components. In this lecture, we detail a graph-based segmentation algorithm. Thanks for your listening and have a nice day.